Good morning, sir. My name is Priyanka from Thought CSC, and my topic is BB84 Single photon in QKD. Now let us discuss about the introduction to BB84 Single photon QKD. The BB84 protocol is a pioneering quantum key distribution scheme developed by Charles Bennett and Gilles Bresson in 1984. Here BB means Charles Bennett and Gilles Bresson. These two are scientists who can develop the BB84 single photon in QKD. It enables two parties to securely generate a shared secret key using principles of quantum mechanics. By using quantum mechanics, in between two parties, they can send the data securely. This protocol is fundamental for secure communication, offering security based on the laws of physics rather than computational assumptions. By using this protocol, we can communicate with others very securely. Now let us discuss about the basic principles of quantum key distribution. Quantum mechanics allows the detection of eavesdropping through the disturbance caused by measurement. The no cloning theorem prevents perfect copying of unknown quantum states, ensuring security. QKD protocols like BB84 leverage these principles to detect any interception attempts during key exchange. Here, eavesdropping means is nothing but the hacker which acts from the user of the computer. When the user wants to send data to the server, in middle the hacker will come and hack the data. By preventing from this, we can use quantum mechanics. The BB84 protocol overview. The protocol involves allies sending single photons encoded in one of two conjugate bases. Here, Alice wants to send photons to conjugate bases of Bob. Bob measures each photon randomly in one of the two bases, matching Alice's encoding with some probability. Bob wants to check each basis randomly, and he wanted to compare both the choices. After transmission, Alice and Bob compare basis choices over a public channel to discard mismatched measurements, forming a raw key. After transmission of Bob, Alice and Bob wants to compare by using the choices over a public channel, and they can discard the mismatched ones and they can keep the matched ones to form the data. Encoding and measurement in BB84. Alice encodes bits in photons using two orthogonal bases such as rectilinear and diagonal. Bob randomly chooses a basic for each photon measurement, which determines the measurement outcome. Correctly matched basis choices yield correlated bits, forming the basis for the secret key. Here, the allies uses two photons like orthogonal basis of rectilinear and diagonal. Rectilinear means straight line, hyphen like that, and the diagonal means cross line like that. The Bob wants to compare by using those symbols. When he can match, he can get the code. Security against eavesdropping. Any eavesdropper attempting to enter a photon introduces detectable errors in the key. If eavesdropper wants to interrupt photons, detectable error will occur in the key. The protocol includes a step for Alice and Bob to estimate the quantum bit error rate. Here, a protocol is sent to the Alice and Bob to estimate the quantum bit error rate. It is also known as QBER. If the quantum bit error rate exceeds a certain threshold, the key is discarded, ensuring security against interception. If we will find the threshold, the key is distracted and ensuring security against interception. Now let us discuss about error correction and privacy amplification. After Rocky generation, Alice and Bob perform error correction to reconcile their keys. After detecting the error in the Alice and Bob, they want to correct the error case. Privacy amplification reduces any partial information an eavesdropper might have gained, strengthening security. These steps are crucial to secure shared secret key suitable for cryptographic use. Partial implementations of BB84 single photon sources are used to ensure that only one photon is transmitted per encoding, minimizing vulnerabilities. Polarization encoding is commonly employed where polarization states represent different bits. Challenges include photon loss, detector efficiency, and maintaining coherence over long distances. Now let us discuss about the advantages of BB84 protocol. It provides provable security rooted in quantum mechanics, unlike classical cryptographic methods. The protocol can detect the presence of an eavesdropper and ensure key integrity. It is adaptable to various communication channels, including optical fibers and free space links. Now let us discuss about the limitations and challenges. Practical issues such as photon loss and detector imperfections can limit the distance and rate of secure key distribution. The requirement for true single photon sources remains technologically demanding. Side channel attacks and implementation flaws force additional security considerations. Future perspectives and developments. Advances in quantum hardware aim to improve source and detector performance for longer distances. Integration with quantum repeaters and networks with enable scalable quantum communication. Ongoing research seeks to enhance the robustness, rate, and practical deployment of BB84 based QKD systems. Thank you.